Hello everyone and welcome back. In today's video, we're going to talk about how this concept of null space that we studied in the previous video can be used to determine whether a set of vectors is linearly independent or linearly dependent. So for example here, I am given three vectors, v1 being 2, 0, 6, v2 being -1, 1, -1, and then the third vector being -2, 3, 0. And the question is, are these vectors linearly independent or are these vectors linearly dependent? So let's think about how we might answer that question. Now, first of all, let's remember what these terms mean. Going back to a few lessons ago, we defined the term linear independence in three different ways. The first way that we understood linear independence was none of the vectors is contained in the span of the others. We also said linear independence means that none of the vectors is a combination of the others. And we also said linear independence means that the n vectors span an n-dimensional space. Let's try and leverage one of these definitions to help us to determine whether the vectors in this set are independent or not. Perspective number one that you could bring to a question like this one is that linear dependence means one vector is a combination of the others. So there are a couple of different possibilities, right? It could be that the first vector is a combination of vectors 2 and 3. It could be that the second vector is a combination of 1 and 3. Or it could be that the third vector is a combination of 1 and 2. If any one of these possibilities is satisfied, the collection would be dependent. Now let's rearrange all three of these equations a little bit. What I'm going to do is rearrange these equations so that instead of having one of the vectors isolated on one side, I have the 0 vector on one side. So I'm going to rearrange this first equation and I'm going to turn it into the form 0 is equal to negative v1 plus c2 v2 plus c3 v3. I'm going to do the same thing with the second possibility. And I'm going to do the same thing with this third possibility. Now, each of these three equations written in this center column of work, each of these three equations could be represented not as a linear combination, but instead as a matrix vector product. Remembering that every single time we see a linear combination, that's the same thing as a matrix vector product, and every time we see a matrix vector product, that can be understood as a matrix equation. So let me take possibility number 1, possibility number 2, and possibility number 3, and write each of these in matrix vector form. So in matrix vector form, I could start, for example, by constructing a matrix A whose columns are the vectors in my collection. So number 1, for example, would be the matrix A times the vector -1 in the first position, then whatever is C2 in the second position, then whatever is C3 in the final position. Negative V1 plus C2 V2 plus C3 V3 is equivalent to the matrix vector product written right here, the columns being the vectors, and then these coefficients becoming this column vector here. This first statement would be this guy equals the 0 vector. Possibility number 2, case number 2, would correspond to that same matrix. the matrix A times these coefficients, C1, -1, and C3. That matrix vector product equaling 0. And the third possibility corresponding to this equation would have a vector C1, C2, and -1. That product equaling the 0 vector on the other side of this equation. Now I want you to notice something. What I want you to notice is that in all three cases, this vector that is being multiplied by the matrix A is in all three cases non-zero. The vector that's being multiplied by the matrix A always has at least one non-zero entry, -1 in some position. So in all three cases, the matrix A has a non-zero vector x in its null space. And so that gives us a way, a pretty convenient way, to check whether a collection of vectors is linearly independent versus linearly dependent. If I construct a matrix A whose columns are equal to the vectors that are in your collection, if I then study that matrix A and row reduce that matrix A and think about its null space, then if the null space has a non-zero vector in it, that means that the vectors must be dependent. If the null space has only the trivial solution, then the vectors must be independent. So let's summarize that conclusion here. To check to see if a collection of vectors is linearly independent, start by constructing a matrix A with those vectors as its columns. Build a matrix A by using the vectors in your collections as the columns. Then study that matrix's null space. If that matrix has a non-zero vector in the null space, that means your vectors are linearly dependent. So there is redundancy in those vectors. If your matrix has only the 0 vector in the null space, then your vectors are linearly independent, and there's no redundancy within that set. So with that method in mind, let's go ahead and return to the motivating example. With these three vectors provided to us, are these guys independent or are these guys dependent? To answer that question, let me go ahead and load these vectors into a matrix, row reduce that matrix, and see what I can say about its null space. First vector becomes the first column, second vector becomes the second column, third vector becomes the third column. Now, there are a couple of different approaches that you can use to study this matrices null space, right? You could use the method that we established in the previous video of augmenting the matrix with 0 and row reducing that augmented matrix, and that will give you a complete comprehensive description of the matrices null space. But that might be a little bit further beyond what we need in this problem, because we're not being asked to describe the null space in full. We're just being asked to check and see whether the null space is just 0 or if the null space is more than just 0. So this might be a good opportunity to utilize the rank nullity theorem from yesterday. Really, what we just want to see is this matrix A destroying any information as it takes vectors in the domain and produces vectors in the range? So if I just look at what is the rank of the matrix A, if I just look at the number of pivot columns in the matrix A and compare that against the total number of columns that A has, just looking at the rank of A should be enough to tell me what is going on in the null space in terms of are there non-zero variables in there or is it just 0? So let's go ahead and look at the rank of A. Okay, here is the row-reduced version of this matrix A, and what I can see is that the rank of this matrix is only 2. So compared to the size of the domain of the matrix A, the size of the range is considerably smaller. The domain is three-dimensional because the matrix A has 3 columns, onto a range that is two-dimensional because the number of pivot columns, the number of essential columns, is only 2. So the difference between those is the dimension of the null space. The null space is going to be one-dimensional, which means that not only does the null space have a non-zero vector inside of it, the null space has an entire line worth of non-zero vectors inside of it. So the null space is more than just 0. And because of that, we can conclude that the vectors v1, v2, v3, forming the columns of the matrix A, this is a dependent set. Not all of the vectors in this list are essential. Not all of the vectors here become pivot columns. Only 2 of the vectors here are essential. And there is a third vector that's corresponding to free variables. Let's do the example one more time on the set of vectors 1, 2, 1, 2, 0, 1, and negative 1, 1, 0. Let's determine whether these vectors are linearly independent or linearly dependent. And to answer that question, I will treat these vectors as columns of a certain matrix. And I will row reduce this matrix, and I will see how many of these columns are essential, how many of these columns are pivot columns. Now, after writing this matrix in reduced row echelon form, we find that this matrix becomes the identity matrix, ones along the diagonal and zeros elsewhere. So this guy has a rank of 3. It has 3 pivot columns. So in this case, all the column vectors are pivot columns. They are essential. None of them are redundant. So that means that they are linearly independent. So that concludes this video. If you have a collection of vectors and you're trying to determine if they are linearly independent or linearly dependent, you can do that by using the vectors to form the columns of a matrix and then investigating the null space of that matrix to determine whether or not that null space has any non-zero vectors inside of it.